delta U is a constant. So H bar is delta U over S. So that means that U prime bar is H bar e to the minus ds. What is my d? T naught. So delta U over S e to the minus T naught S. So does everybody understand that the Laplace, why this is the Laplace transform of the input? Okay, so that's step one. We found U prime bar. And careful, T and S never mix, but this is not T, that's a number. The variable T and the variable S should never appear in the same equation. All right, step two, Y prime bar is GU U prime bar. In other words, K over tau S plus 1 e to the minus ds times delta U over S e to the minus T naught S. And let's divide by tau to make it a regular form that you're more used to. So I can rewrite this as K over tau S plus 1 over tau, that's this part here, and S from this part, and delta U from this part, and then I have e to the minus ds times e to the minus T naught S. I have product of two e's. I have e to the minus T naught S that comes from the input, and then e to the minus ds that comes from the transfer function. You should all remember that e to the a times e to the b is e to the a plus b. So we can combine the two together to write that Y prime bar equals K over tau delta U over S plus 1 over tau e to S times S e to the minus T naught plus D times S. So that's the end of step two. Step two, step one. Any questions? All right, step three. Dictionary. What do I have? I have some function of S times e to the minus a constant times S. That constant parenthesis plays the role of the delay in the dictionary. So using the dictionary delay entry, we have that y prime of t is equal 0 for t less than what? We will tell. Okay, someone raise a hand. Shannon?
Less than T naught plus D.
Yeah, well, I has to be able to hear you. Shannon said T naught plus D. Okay? It's whatever multiplies the S. So T naught plus D. That makes sense. Obviously, T naught is the time I made the step change. Shouldn't this point before the step change happened, and since I have a delay D, it will not sense, it will not show anything in the output until T after the time made the step change. In other words, T naught plus D. And for the other one is H of T minus T naught plus D, which plays the role of the delay, for T greater than T naught plus D. And what can we say about the H? That H bar is whatever multiplies the e to the minus something else. So H bar is whatever multiplies the e to the minus. So this is the h bar. So where h bar equals, and we have here k over tau delta u times s plus 1 over tau times s. That's not in our dictionary, but what can we do to find the inverse? In case somebody's in the dictionary, partial fractions expansion. Is this a tough partial fractions expansion? All right. So let me have a volunteer tell me what partial fractions expansion are, right?
C1, wait, is there, yeah.
Okay, one, go ahead.
C11 divided by S.
Okay, let's have this side first.
My, what, S plus 1 over tau plus C21 divided by S.
Pole, not pole, denominator. Pole is only if it belongs to the transfer function. In this case, up to the pole. Minus 1 over tau is one denominator root. Root 1 is minus 1 over tau. Root 2 is 0. So S minus root 1, S minus root 1. And how can I find C11 and C21? The quick and easy method. So for C11, someone raise their hand, hasn't spoken.
We have S plus 1 over tau.
What value do I use?
We use negative 1 over tau.
Exactly. So I cover the denominator of C11, and I use what makes the denominator 0, minus 1 over tau. So that's going to be K over tau times delta U divided by S minus 1 over tau by minus 1 over tau, which makes equal to 1 over tau cancels out minus K delta U. Okay, someone else tell me C21. Okay, Ash.
Oh, okay, you're going to cover up the denominator S,
Uh-huh.
and then you're going to let S in the other part equal 0.
Exactly. And so that leaves me K over tau delta U divided by 1 over tau. And then 1 over tau cancels out, so plus K delta U. So H bar is equal to minus K delta U over S plus 1 over tau plus K delta U over S. Both are now easy in the dictionary. So using the dictionary, minus K delta U is a constant. Okay? So I can factor, and 1 over S plus 1 over tau is 1 over S plus A being 1 over tau. So remember the dictionary, we have that e to the minus AT becomes 1 over S plus 1. So 1 plus 1 over tau. Okay? So H of t is going to be minus K delta U times e to the minus 1 over tau times t. What about K delta U over S? How about someone on the right side of the class? K delta U over S, what is the inverse of that? Say, Mohammed?
It's just, yeah.
I have K delta U divided by S. So what's the inverse of K delta U divided by S?
K delta U.
K delta U, exactly. I wasn't hitting the K. I was hitting just over here, so that's why I wanted to do it. That's it. Hey, and we can factor k delta u. So we can write as k delta u times 1 minus e to the minus t divided by the time constant. That's h of t. What should I have there? H of t minus t naught plus d. So the final y prime of t, and this is an equation that should definitely be in your cheat sheet for the second exam. We'll be using this equation a lot, but I may actually derive something else similarly, so don't rely only on that. So that's 0 for t less than t naught plus d, and k delta u times 1 minus e to the minus t minus t naught plus d, all that divided by down for t greater than or equal to t naught plus d. I could have put that in your examples. Okay, you should have been able to do it.
Wait, what?
I could have put that problem into your first exam because there's nothing new in what we just talked about. I almost did it.
No, don't do it.
Okay. Everybody clear? Now let's look at what this response entails. And actually before I do that, I want to be able to use the class notes also. There's one difference to what I just did and the class notes. The class notes are for t naught being equal to 0. So for class notes, you don't have t naught appearing here. You say for t less than d, 0. For t greater than d, t minus d here. Because the step change in the class note happens at time 0. If for some reason you were not using what we did in lecture, you're using the post class notes. How can you use the post class notes if I give you a problem and tell you the step change didn't happen at time 0, happened at time 42? How would you use the class notes if t naught is 42 instead of 0? The class notes are for t naught equals 0. Very simple.
Subtracting the time from all.
Exactly, from every time. Method will be using certain times. So anytime you measure from the experimental data, from a response curve, I don't have a response curve. Okay, I don't have a good response curve. But anytime you're measuring, just subtract t naught and change the time scale. Then the step change happen at time 0. So either way is fine with me. I prefer to do it this way because you don't have to do any subtraction. If the step change happen at 9:50 a.m., you just have 9:50 a.m. for t naught. Okay? Otherwise, subtract 9:50 a.m. from all your times and proceed that way. All right. Now let's put. Okay, I'll put on this equation. How about 4 stars for remember? So this is the 4-star equation. Used a lot today. What does it look like? So what the 4-star equation looks like, well, we know a lot about the qualitative response, so we should be able to use what we have learned about qualitative responses to see immediately what it looks like. So u changes at time t naught by delta u. Let's say y is down below. Here is the time axis. Oh, that's y, you just simply add y naught. Y would be, yeah, good morning. Y of t would be y naught here, okay, y naught plus 0, and y naught plus, okay, because always the actual method output is the nominal value plus the deviation. Okay, let's go back here. So the actual, the y of the model is going to be staying at y naught until time t naught plus d. Until time t naught plus d, it's y naught plus 0, in other words, y naught. Everybody again? Peter? Okay. So we stay at y naught until that time. Where is going to be our new steady state?
T naught plus D.
Now, what value would be the new steady state?
Delta U plus U.
Y. What's the new steady state of y?
What time is the time conflict?
Does it matter? Steady state value. How can I find the steady state value of this, having this equation? Say it. Who said it? Was it Colton? Say it.
The limit as t goes to infinity?
Exactly. Thank you, Colton. Steady state says t goes to infinity. What happens if t goes to infinity? This does, right? E to the minus infinity becomes 0. So it becomes y naught plus k delta u. So here is y naught. It will end up at y naught plus k delta u. If I used gu of 0 times, what's the input change? Delta u. Another way you can see that y prime infinity, right, is gu of 0 times u prime infinity. In other words, gu of 0 delta u. In other words, k over tau 0 plus 1 times delta u. In other words, k delta u. And of course, y infinity is y naught plus y prime infinity, the actual, the nominal value plus the deviation. So in other words, y naught plus k delta u. So either by taking the limit, as time goes to infinity, as Colton told us, or by using the finite theorem. So we'll end up there. Will we have a corner? How many poles, how many zeros are? No zeros. How many poles?
2.
1. So 1 pole, no zeros. Do I have a corner?
Yes.
Do I have anything like inverse response? No. We have no zeros, so then we don't have a positive zero. So with a corner, do we have any oscillations? No, not even mathematical ones, right? I have only 1 pole, and that's real. Minus 1 over tau. So what it will look like is, with a corner, it will take off and go. So that's what the first order plus time delay response looks like. So let's understand the role of each parameter. The time delay tells us this distance between t naught and the corner is the time delay. Okay, that tells us when the system starts changing. How much is the total change in the system from beginning value to new steady state? Well, the new value is y naught plus k delta u.